Okay, now in practical application of current mirror, early voltage is assumed to be, in practical application of current mirror, your early voltage is assumed to be, first one infinite, second one zero, unity, none of the mentioned. Let us see the explanation. In the previous slides or lectures, we have seen that what is meant by early voltage. Early voltage is what here? Early voltage is a voltage which will describe how your output current is going to be varying. So now here output current is varying means what? We have seen that even the equations in the previous lecture, that your early voltage is related with your I reference. I reference, whenever it comes the topic of I reference and I out, it means that you are dealing with a current mirror. Okay, you are dealing with a current mirror. So now see the options. Early voltage is assumed to be infinite, so that the output resistance tends to infinity and output current is constant. Is it okay, ma'am? Your early voltage has to be always infinite. Your early voltage has to be always infinite. Why the early voltage has to be always infinite? Because whenever the early voltage is very infinite, the output resistor also will be infinite. Whenever the output resistance is infinite, so you're going to get the output current which is going to be constant. So see here now. See the formula here. We have seen the formula. This formula, what is that? RO equal to V into I reference. RO equal to V into I reference. So see now. Early voltage means what? Your early voltage is nothing else but it is RO equal to VA into I reference. So VA is equal to what? Your VA is equal to RO into I reference. So ultimately, whenever this one is infinite, whenever this one is infinite, the RO also will become infinite. Whenever the RO is infinite, so ultimately your resistance will become, whenever the output resistance is very high, because of the output high resistance, the output current also will be constant. The output current will be constant. Why? Because the resistance is high, there will be no movement of the current or no flow of the current through that particular path. So output current also will be constant. So ultimately, in practical applications of a current mirror, your early voltage has to be always very high. Why the early voltage has to be very high? Because your current mirror has to maintain the constant current across the two branches or the two parts of the what is that differential amplifier. One branch is nothing else but the I reference path, other branch is nothing else but the I output path. So if the current is constant, then only you'll be having the main the current mirror will be valid. So in order to have the validation of the current mirror, your early voltage has to be constant. As per the formula we have just now seen, if the early voltage is constant, your output resistance also will be constant. Whenever the output resistance is constant, the current across that output resistor will be constant. Sorry, excuse me. Early voltage has to be very infinite. It has to be infinite. Whenever the early voltage is infinite, then your output resistance also will be infinite. If the output resistance is infinite, then only the output current is going to be constant. Okay, fine. So your option A is the correct one. Second one, if the reference and the collector currents are 0.539 milliampere, if the reference and collector current are 0.539 milliamperes and 0.49 milliampere respectively, then how many transistors are used in current repeater circuit? Assume beta is equal to 150. Assume beta is equal to 150. This is an important one. Try to remember the formula for this one. We are supposed to, this kind of questions will be asked basically in terms of your gate exams. So we are supposed to find out a number of transistors over here. So formula is what? Current equation is given as IC equal to I reference into beta upon beta plus 1 plus n here. Beta plus 1 plus n, where n is nothing else but the number of transistors. N is the number of transistors, and I reference is given to us as 0.539 milliamperes, and your IC, that's the collector current, is given as 0.49 milliampere. When you substitute these values over here, so ultimately you're going to get, even the beta is given as 150. So when you substitute here, you're going to get the value of n is equal to 14. So you're supposed to remember you are supposed to remember this particular formula. I say, if you want to calculate the number of resistors, if you want to calculate the number of transistors, then the formula is IC equal to I reference into beta upon beta plus 1 plus n, where n denotes the number of transistors. When you substitute all the given values, there is nothing unknown to us. Only the one term is unknown, that's the number of transistors, which is supposed to be found out. So you substitute all the known values. Beta is 150, I reference is equal to 0.539 and IC equal to 0.49. When you substitute, it's a direct substitution. When you substitute, you get your answer to be 14. So that's a option B is the correct one. Option B is the correct one. So it's a very important kind of problem. Try to remember this formula. It is useful as per the point of GATE exams also. Which current source exhibit a very high output resistance? Now we are supposed to see See, up to now we have seen that a current source will be having a very high output resistance. Means what? Just now we have studied in the second or third numerical or the MCQ, your current source will be having a high output resistance and also it will be having a very high early voltage and the output resistance will be infinite. Why it has to be infinite? Because in order to have the constant current. So now we are supposed to study among different current sources which is the best one to have the higher output resistance. So now options are given to us: simple current mirror, Wilson current mirror, Widler current mirror, and all of them mentioned. So these are the current mirrors which are basically used in the research work to find out or to maintain the constant current, in the circuits. So option B will be the correct one. That's a Wilson current mirror is a correct option. So let us see the explanation. What is the explanation here? So here explanation is that we can see that the output resistance of a Wilson current mirror is subsequently greater than beta times of output resistance divided by 2 than the simple and the Widler current mirror. So here CMM, I'll try to describe you how this Wilson current mirror will be there, and again Widler current mirror will be there. See, there's only small differences here between the Wilson and Widler current mirrors. So those differences I'll tell you. See, if you're talking about a Wilson current mirror, where is my pen? Okay, fine. Here is my pen. See, if I'm talking about Wilson current mirror, if this is my resistance, I'll be having my transistor here in this way, and again I'll be having another transistor over here in this way. Excuse me, it should be like this over here. It is not from this part. It has to come from the emitter. So the emitter will again trigger the this one collector of this second transistor. So now this is now here again you will be having the this junction here. The same kind of transistors will be again present in the other side. So it is nothing, since it's a current mirror, we know that both it will be having the two branches. Probably there will be two branches, and we know how it is connected. Both the bases will be connected, and again here is another one. Another transistor will be there. The transistor here which is connected to the emitter of this one. So now see, these both are connected here. Both are connected, and then this one is connected to the resistor in the above way. We know what is this one. The current which flows in this one. We call it as a I reference. As per the concept of current mirror, this is the I reference, and the current which flows in this one, it is called as an I output current. So now here we are having the two branches where I reference and I outputs are there. So what we have studied, it's a current mirror means what? It is a connection between these terminals, the gate terminal and drain terminal. So this is a connection like this. We'll be having a connection. So this kind of this is a simple current mirror. We can call it as a, in fact I should call it, instead of calling it as a simple current, I should call it as a Widler current mirror. In the difference between the Wilson current mirror and Widler current mirror is that, see now, if you are having these two kinds of current mirrors, current mirror means what? It is a connection between the output terminal, there's a drain terminal. In fact, if I talk about BJT, it's a collector terminal and the base terminals. Okay, so now if current mirror means there will be a connection, there is short circuit connection, sorry, there is a this kind of connection between the collector terminal and the base terminal. So this kind of connections we call as the current mirrors. So now if you are having two kinds of current mirrors like this, we call this one as a Wilson current mirror. It is called as what, ma? It is called as a Wilson current mirror. So now what is a Widler current mirror? I'm just mentioning it as CM current mirror. Then what is a Widler current mirror? It is similar to this one. The only difference is that you will not be having the cascading of the transistors just like which was in the previous case. You'll be having only one set of transistors which are connected like this. So now this kind of connections, where again bottom will be here, I need to draw here one ground terminal, here also one ground terminal, where the bases are connected directly here, and this one will be given to the resistor, and here it is a I reference. It is called as an I reference current which is flowing through the mirror circuit, and this will be the reflection of that I reference, that's a I output. So this is a reflection and that's a current which is flowing in the one. So now this, if I connect this part and this part, now this becomes as what? Now this circuit is called as an Widler current mirror. The earlier one is called as an Wilson, and now this one is called as an Widler current mirror. Excuse me, please. I'm unable to write this one. I hope it's clear to you, but anyway, this one is called as an Widler current mirror. If you have this kind of only one current mirror is present over here, in this way, we call it as a Widler current mirror. If you are having the cascading kind of circuits in the previous one which I have drawn, that one we call it as a Wilson current mirror. So now see now, this is a difference now. Now what's the explanation? The output resistance of a Wilson current mirror is subsequently greater than the beta times of the output resistance divided by 2 than the simple or Widler current mirror. Why? Because this kind of setup will always will have the greater this kind of setup will always have the greater output what is that output resistance than compared to the Wilson current mirror. So ultimately what's our main aim? Our main aim is that the current mirror should have the infinite output resistance or very high output resistance. So now this kind of setup will always give us a very high output resistance than compared to the single kind of connections of a Widler current mirror or simple current mirror. So ultimately your option B will be the correct one. Why? Because the Wilson current mirror will exhibit very high output resistance than compared to the what is the other one, Widler current mirror or simple current mirror. Then the next one, what will be the overall gain in the Darlington circuit? This Darlington circuits we have studied in the EDCs. Now let us see, let us apply the gain with a gain kind of concept to the Darlington circuits. What will be the overall gain in Darlington circuit if an individual transistor gain is 200? Each one transistor's gain is given to us 200. What is a Darlington circuit? Darlington circuit is nothing else but it's a combination of two bipolar circuits. Means how it is connected, where the first transistor's emitter will be driving the base of the second transistor. That's a Darlington circuit. And again both the collectors will be connected at one particular point only. Darlington circuit means what I told just now, the base. I'm unable to find this cursor. Okay, here the Darlington circuit is what? The emitter of the first transistor will be driving the base of the second transistor. You can see now this is an NPN transistor. Even this is what? It's a PNP transistor. Here also ultimately see now it is driven like this. So now here basically we'll take NPN into concentration because of its high mobility concept. So in the high mobility concept, you can see now here in the NPN one, the emitter of the first transistor, TR is the first transistor, transistor 1 is driving the base of the second transistor. So this kind of combination, these kind of combinations, we call it as a Darlington circuit combination. And the outputs, both the collector currents are connected at one particular point, and it will be termed as a IC value. So this kind of concepts we call as a Darlington circuit. So see now, a Darlington transistor configuration of two bipolar transistors offer increased current switching for a given base current. Why? Because ultimately it is this particular transistor is having its own it's having its own base current, and another current is flowing from the emitter to this another transistor. So now it will be having a increased switching current. The switching current has been increased here. The Darlington circuit, or the Darlington transistor, named after its inventor Sidney Darlington, is a special kind of arrangement where two standard NPN transistors or two standard PNP transistors connected together. How they are connected here? The emitter of the one transistor will be connected to the base of the another transistor. The emitter of the one transistor is connected to the base of the another transistor. Why we are connecting this one? In order to produce more sensitive transistor, which will have the greater and larger current gain. In order to have the larger current gains, we are making this kind of connections. By this kind of connections, you will be getting the more amount of current gains, which are used in the applications of current amplifications wherever it is required. So now let us apply this for this concept you have studied. In order to get the large amount of current gain, what you are supposed to do? You are supposed to apply the Darlington circuit. What is the Darlington circuit? In the Darlington circuit, the base of the emitter of the first transistor will be connected to the base of the another transistor. Means what? The emitter of the first transistor is triggering the base of the second transistor. So now let us calculate what is the overall gain of a Darlington circuit. So see now, if one of the transistors, see now, it is mentioned that the one transistor's gain, here it is given that A equal to 200. Each one transistor's gain is equal to 200. Means ultimately each transistor is having a gain of 200 plus 200. There's a 400 gain will be there. So now let us see how to calculate the total overall gain of this Darlington circuit. The overall current gain is equal to beta. Overall current gain beta is equal to beta 1 into beta 2. That is nothing else but you are trying to multiply the current gain of individual transistors. Current gains have been given to us. So individual transistor is having a current gain of 200. So how to get the total current gain? The total current gain is nothing else but it's a multiplication of the two current gains. Beta is equal to beta 1 into beta 2. So you get ultimately beta is equal to 200 into 200, that is equal to 40,000. So the value of beta is equal to 40,000. Your option B will be the correct answer. Option B is the correct answer. I hope it's clear to you. Is it clear, ma?
Yes, sir.
Next one. To increase the input resistance in a differential amplifier. To increase the input resistance in a differential amplifier, replace the transistor by what you are supposed to replace. You are supposed to increase the input resistance in a differential amplifier, replace the transistor by. So here you will be using a Darlington pair. Darlington pair will be used to replace the transistor in order to have the input resistance. So now let us see now. Higher the value of input resistance can be obtained by using a Darlington pair in place of transistor. Just now we have seen that how the input resistance can be increased and how we can maintain a current gain there. You will be having a greater current gain. Means what? Current gain is greater. So that means what? Ultimately the gain is a constant term. So current, you are getting a constant current value over there. So constant current means what? It's a input resistance is completely very high. Current is not changing. Current is not changing means what? Ultimately the resistance is also very high. Where does this current is not changing? Current is not changing at the input terminal only. Why? Because why should I call it as an input terminal? Why? Because the emitter of the first transistor is driving the base of the second transistor. Base is nothing else but it's an input terminal. So ultimately, if you are having a constant current gain there, it means that you have that particular circuit is having a highest input resistance. So that can be done with the help of what? Your Darlington pair. So answer will be Darlington pair. Next one. What is the drawback in using Darlington pair in differential amplifier? So let us see now what's the drawback here now. Due to the cascading stage of Darlington differential pair or Darlington differential amplifier will offset higher offset voltage, which is 2 times larger than the ordinary 2 transistor used in the differential amplifier CMR. Here in this Darlington pair, you are going to get the highest higher value of current gains. But when it comes to the voltage gain, if you are trying to find out the voltage gain, we know that at the input terminal, offsets will be present. What is an offset? Offset is nothing else but it's an unwanted noise which is present at the input, even though if you do not supply some input signal. Even though whenever the input signal is not supplied, you are going to get some unwanted noise. That unwanted noise only has been amplified at the output and you will be getting some output. Means what? You are not applying some input, but you are getting some output. That output only we call it as OOT. You have studied that OOT, one term called OOT. Excuse me. You have studied one term called OOT. VOOT. OOT. What is this one? It's a total output offset voltage. It's a total output offset voltage, or else which is similar to VOO, output offset voltage. Output offset voltage. What is this output offset voltage? Even though if you do not supply some input to the amplifier is producing some output. That output only is called as an offset voltage. Since it is obtained at the output, we call it an offset output voltage. So if you find out the total offset voltage at the output, we call it a OOT, total output offset voltage. So see now, whenever you connect in the cascading, this offset noise has been amplified from the first stage to the second stage. Then ultimately the noise is amplified. The efficiency of the transistor also will be efficiency of the amplifier also will be decreased. So that's why this is one of the major drawback of the Darlington pair. The major drawback of Darlington pair is what? It will have a very higher offsets. How many times? It will be 2 times of a transistors. It will be 2 times of a transistors. So your answer D will be correct one. That's a high offset voltage. Darlington pair will have a greater current gain. Whenever you want any current amplification kind of application, you can use a Darlington pair. But whenever you go for this voltage amplification, voltage gains, then this is having a disadvantage. That is, it will be having a high offset voltage. Means it will whatever the output you get at the circuit, it will be an inculcation or it is an added signal of noise with the output. The noise also will be transmitted from one stage of a Darlington pair to the another stage of a Darlington pair. So that's why it's a major disadvantage. The second one, determine the amount of shift happens in the level shifter. Determine the amount of shift happens in the level shifter. So let us see this one. There are some options have been given to us. Let us see what is the correct one. Level shifter. What is a level shifter? Level shifter, we know that it's a basically a simple type of emitter follower. We have seen this level shifter in the previous lectures of a block diagram of a operational amplifier. Operational amplifier will have what? Differential amplifier will be the input stage, then the gain amplifier, voltage amplifier, the third is a level shifter, then final will be the output amplification. The third one, level shifter, is nothing else but it's a emitter follower. So level shifter is what? It's an emitter follower circuit. So now here this level shifter, let us see how to calculate the amount of level shifter. Hence level shifter also acts as a buffer to isolate the high gain stage from the output stage. What is buffer, ma'am? What's the buffer? Buffer is nothing else but which will pass the signal from input to output. It will simply pass the signal from input to output. So now therefore the amount of shift obtained is nothing else but that is given by the formula as that. Where is this one? The output is equal to Vout is equal to V minus Vi is equal to minus VBE. So minus VBE is what? VBE is nothing else but your base emitter voltage. What base emitter voltage? It's the minimum amount of voltage to turn on the transistor. So ultimately it is equal to 0.7. So minus 0.7 will be your level shifter voltage. The amount of shift happens in the level shifter will be this one. That is option C is the correct one. Option C is the correct one in this case. Introducing the FET differential amplifier pair at the input stage of differential amplifier produces dash. If you are introducing a FET field effect transistor differential amplifier pair at the input stage of a differential amplifier produces what? So see now, let us see the option. The input resistance of an order of 10 to the power of 12 ohms is possible with JFET at the input stage of a differential amplifier. Whenever you try to design any differential amplifier with the help of JFET junction field effect transistor, that particular junction field effect transistor will be having the greater input resistance. We know that op-amp should have the infinite or very high input resistance. Because of that high input resistance only, the current will not enter into the terminals of the op-amp. So now your op-amp will be having a high input resistance. So that was, so ultimately what, if you introduce a FET as a differential amplifier, it will have a very high greater input resistance. So option B is the correct one. Option B is the correct one. High input resistance will be the final thing. So if you introduce this one, the input resistance will be increased. That is to the value of, sometimes they might even ask this one. Try to remember this one. Whenever the FET is introduced at the differential amplifier, what is the input resistance at the input of the op-amp? That is 10 to the power of 12 ohms. 10 to the power of 12 ohms is a input resistance is being formed whenever JFET is being used at the input stage of a differential amplifier. Why active load is used in amplifier to obtain the large gain in intermediate stage of an amplifier? Why we are using an active load is used in an amplifier to obtain a large gain in intermediate stage of an amplifier. So see now, active load. Why do we are using active load? Ultimately load is nothing else but it's a parameter where we obtain our output voltage. At the loads only we will be obtaining our output voltage. So why we are using the active loads? Let us see now. In order to increase the gain, usually large collector resistor value is needed. Just now we have seen in the previous slides that collector current should be collector current resistance should be very large, as the gain is proportional to the load resistor. Gain is directly proportional. Your gain is directly proportional to your resistor value. So that's why if you want to get this value, a higher value of the gains, so the load resistor also should be very high. Your what is this load resistor? Load resistor is nothing else but ultimately I can say that it is a resistor which is present at the output. So you can say that it's an output resistor. So if the resistor value is very high, the gain also will be very high. Gain is also very high. However, due to the limitation of maximum value of load resistor, active loads are used in amplifier to obtain the larger gain in intermediate stage of an amplifier. Okay, so in order to get the higher value of the gains, we will be using a load resistor which is very high, and that load resistor is been used here as an active load. It can be active load anything. It can be your resistor, any passive element, any passive element. Why? Because your outputs are obtained across the passive elements, so it can be any passive elements with a higher value. In order to obtain very high voltage gain, we are using the active loads in order to obtain the very high voltage gains. So answer A is the correct one. Then the next one, which circuit is used as an active load for an amplifier? Which circuit is used as an active load for an amplifier? What is an active load? Just now we have studied in the previous slide. Active load is a any passive element which is equivalent to the resistor. So now we have studied in the previous circuits here now. Widler current source. Widler current source we have studied. In the Widler current source, what happens? In the Widler current source, the current mirror will be there, but it will not be very high as compared to the other one. Then what is the Darlington current mirror? Darlington current pair. In the Darlington current pair, the current gain will be very high. Current gain is high, means current is not constant. Whenever it comes to the current mirror, what is the current mirror? Current mirror is a circuit where the current is going to be constant in both the branches of the circuit. If a current is constant means what? That particular current mirror is acting as a resistor. So now this particular current mirror is acting as a resistor means what? Ultimately that is acting as a load. We have studied that your load is nothing else, but it can be any kind of the passive element. So ultimately in the AC circuits we'll be using the resistors as a loads. So now here current mirror is a circuit which will be having a constant current. Constant current means what? Current is not changing, means there is some kind of parameter which is trying to vary, that which is opposing the variation of the current. That anything which opposes the variation of current is nothing else but resistor. So now this current mirror is equivalent to the resistor. So ultimately that resistor is nothing else but equivalent to active load. So your option C will be the correct one. Let us see the explanation now here. Current mirror has a DC resistance of an order of few kilo ohms, has a quiescent voltage across is a fraction of the supply voltage and current in the milliampere. This one we have studied in the basics, that your quiescent voltage is always, this is a definition of the quiescent voltage. This definition of quiescent voltage of a current mirror is what? The quiescent voltage in the current mirror will be always a fraction of supply voltage and the current in the milliamperes. So now current mirror exactly the explanation of this one doesn't tell why the current mirror is used here. The explanation, whatever the explanation I have given, that's the correct one. Means this current mirror is will be having a constant current. That constant current means what? It's not, current is not varying. If a current is not varying means what? There is some kind of element which is trying to oppose the variation of the current. What is the element which opposes the variation of current? It's a resistor. So resistor is taken as equivalent to the active load. Load is nothing else but, in the AC circuits almost all the load voltages are obtained across the loads. That loads, one of the load is a resistor over here. So ultimately you can take that load is equivalent to your current mirror. So option C is the correct one.